Hey, BC Calc students, this is day 39, and day 39, you can see right at the top, it's all review today. So even though I will model some of these questions in today's video, I would certainly encourage you to try any and or all of these questions on your own because they are all things that at this point in theory, we should know how to do. So what is this going to help you prepare for? Well, on tomorrow's quiz, we've got the following topics related to rates, including some angles in there, going back to day 34. We've got slope fields. That was pretty recent for us on day 38. We've done a lot with max min, solving differential equations. You can see that right down below here from day 37. And just a quick note is that it's mostly chapter 4 with derivative applications, but certainly we could expect some other cumulative topics. And if I have anything else specific that I want to include about that, I will let you know next time I see you in person. So taking a look at the first question, this is actually an old homework question on differential equations. So if you take a look at this third order differential equation, given the third derivative equals 6 with the following initial conditions when x equals 0. So given those initial conditions, see if you can come up with what y is based on this scenario here. And then I will go over my result next time I see you in class. So this is something that, again, if it looks familiar, I think it is directly from the textbook on its number 34 on an old homework, but we'll recap that next time we're together. So I will start by doing the next question with you, and this is a max min practice question. So what are the dimensions of the rectangular plot of land of greatest area? So we're trying to maximize area here. That can be laid out within a triangle base of 36 feet and an altitude of 12 feet. Assume that one length of the rectangle must be on the base of the triangle. So you can see that in the scenario, we know that the base length of this triangle that I've drawn is 36 feet. And we know that the altitude in total at this length right here is 12 feet. Okay. So based on that, we know that one length of the rectangle must be on the base of the triangle. So there's my length. And then when I draw these width parts up, those heights, wherever that hits the other legs of the triangle, that's the triangle that is inscribed within this triangle. Okay. So now that we have all this set up, we need to be able to determine an area function to model the area of that rectangle. So the area, if we call the base of the rectangle x, and we'll call the height of the rectangle y, the area is just x by y. So in order to maximize that, we're certainly going to have to use the given information to be able to develop, can I represent the height of the rectangle y somehow in terms of x? And given the dimensions that we have here for the altitude and the base length, we can represent what y is in terms of x. So what we're going to wind up doing is creating a proportion, because it might be a little tough to tell, but we do have some similar triangles here. And the similar triangles that I'm going to use are, I'm going to use the big triangle on the outside. Okay, so my green triangle whose base length is 36 and height there is 12. I'm going to compare that to this triangle right here. Okay, and we know that those triangles are similar because of properties of parallel lines here, and we can definitely prove by angle-angle similarity if needed that this triangle is similar to the big one that surrounds it. Okay, so what I'm going to wind up doing is, because I know the altitude and base of the big triangle on the outside, I'm going to take the altitude over the base, and because similar triangles have proportional corresponding side lengths, I want to compare that to the altitude and then the base of the similar triangle within it. So if I can set up some sort of proportion, I'll be able to use this proportion, I hope, in order to get y in terms of x. So for the big triangle on the outside, we know that the ratio of altitude over base is 12 over 36. So now looking at this red triangle here, we have to compare its altitude to the base right here. And the base is going to be easier for us to determine because the base is actually just x, isn't it, right? It's the same length as the base of the rectangle there. So we know that the base is x. But to get the altitude, it shouldn't be too much more challenging for us, because if this is y, we know that this part is y. And if the total altitude is 12, then the altitude of my triangle up at the top here is 12 minus y. So set that to be this altitude up here. Okay. So then from there, it's just a quick cross multiplication step, and then we'll get y in terms of x. So when I do that, 36 times 12 minus y would wind up becoming 432 minus 36y. That equals 12x. So from here, if we do some quick rearranging and getting y alone here, subtract the 432, divide by negative 36. In the end, you'll find that y is equal to 12 minus x over 3. Okay. So now that I have that expression, now our job is much, much simpler. And I think the tough part about this one is certainly setting up your own diagram. But once you've decided that, calling the base x and the height y, creating a proportion to get the representation for this altitude and base such that we can get y in terms of x. Okay, now that we've established all that though, y is going to be 12 minus x over 3. And what I've seen just based on some of your work in other examples is that a lot of you at this point might choose to do product rule, which there's certainly nothing against that. It might make your job easier if you actually just distribute the x in, make it 12x minus x squared over 3, and now you can just apply power rule to find the derivative. So the derivative in this case, a prime, would be 12 minus, drop that exponent down, it would be 2/3 x to the first. So to find our critical value, we'll set that equal to 0, and we're going to get 2/3 x is equal to 12. Multiply both sides by 3/2, and we get that x is equal to 18 is my critical value. Now, remember that we always want to justify our maxes and mins here. So to justify whether or not x equals 18 is a max, you can do one of two things. First derivative test, right? Put that on a number line, test on either side, and the first derivative, which should be pretty easy for us to do, and then use our justification statement. But keep in mind, because the second derivative is so easy to find in this one, a double prime is just negative 2/3. What does that imply if the second derivative is always negative? Always negative implies that this graph is concave down everywhere. Therefore, we have a relative max at that critical point at x equals 18. Perfect. So now that I've justified that that is in fact a relative max using the second derivative test, which was easy enough to do, what is the question? What are the dimensions of the rectangular plot? So we know that x is 18. And if x is 18, we can go back and re-sub in to figure out what y is, right? So 18 over 3 is 6. 12 minus 6 would be 6 in that case. So the dimensions that produce that greatest area would be an 18 by 6 rectangle. Okay. So the hardest part about this one, probably the picture initially. And then once we have that, recognizing the similar triangles to get y in terms of x. But once we can do all that, then the actual calculus behind this question should be pretty easy for us to recognize. All right, moving on to the related rates question right below it. I'll do this one as well. This was a question on an old homework, but I think we'd benefit from seeing this example done out together. So there's a question about an airplane 10 miles high that passes directly overhead at 600 miles per hour. How fast is the angle of elevation changing to the plane 1 minute later? So we have this plane that's flying. And then 1 minute later, we're going to be observing the plane from a point on the ground. And I want to know at that specific time, how fast is the angle of elevation changing from that location on the ground? Okay, so the airplane's 10 miles high, so that's going to stay constant for the entire time that this plane is traveling. So that height there is 10. It passes directly overhead at 600 miles per hour, so that's going to be our dx dt in this case. Dx dt is 600 miles per hour. So if we're looking at our given, we're given dx dt is 600. We're given that if we want to call that length y is 10. How fast is the angle of elevation changing 1 minute later? So we want d theta dt. Remember that for any trig application, we got to have radians for d theta dt when the time is 1 minute later. Okay. Well, since the plane is flying at 600 miles per hour, we can know that if we divide that by 60, because we have 60 minutes in an hour, we know that 1 minute later that the distance x is 10. So we're also going to use that as a piece of information to be able to set this up. So to set the stage initially, since this is going to be changing, we want to make sure that we define it as x initially. So to set this up, because it's a nice right triangle, you certainly don't need any kind of law of cosines like we've seen in other applications. There's going to be some SOHCAHTOA, a right triangle trig. So we've got tan theta is equal to 10 over x. All right, and now that I have that, we might want to maybe just quickly write this as 10x to the negative first, so that when I find the derivative, it's a little bit easier. So the derivative of the left side, derivative of tan, is secant squared theta, d theta dt. And then over here, we're going to get negative 10 x to the negative second. Maybe I'll throw that downstairs now, x squared, and then dx dt. Okay, so what we're solving for in the end was d theta dt, so I see where that is. I know that we're doing that when x equals 10 and dx dt is 600. So if we start plugging in some of that information here, we know that the right side is negative 10 over 10 squared times 600. And then over here, d theta dt is what I'm looking for, but apparently I should know something about sec squared of the angle theta. So at this specific moment in time, when x is 10, what is theta? There's our other hidden unknown that we're going to have to establish, right? So theta at this moment, if I do tan theta equals 10 over 10, which is 1, we know that theta is actually 45 degrees or pi over 4. So this side's going to become secant squared of pi over 4. So if we think about in this setup here, this would be 10 radical 2, right? If we think of the special right triangle properties, secant would be hypotenuse over adjacent. So secant of pi over 4 is radical 2. That's what that ratio would reduce to. And because I'm squaring that, this just becomes 2 d theta dt. So that looks like a fairly easy, quick substitution there. But it actually wasn't quite as easy as that all seemed, right? We had to think back to, wait, this is not even a known value yet. Use our right triangle trig to get that theta is pi over 4. And then secant of that value, hypotenuse over adjacent, would reduce to radical 2. Square it to get the 2. So then finally, d theta dt would be, well, let's see, over here, 100 goes into 600. We'll be left with 6. So that's negative 60 there. Negative 60 divided by 2 would be negative 30. And this is radians per hour would be the rate at which the angle is changing at that given moment. Okay. And it makes sense that it's decreasing, right? I mean, initially, when the plane flies overhead, you can see that as the plane travels, the angle is slowly decreasing for our angle of elevation there. Okay. So I like that question. I think it's kind of cool in terms of just using right triangle trig instead of, again, what we've seen with a lot of cosines. But there are definitely a lot of hidden unknowns that we have to be careful and cautious about that we're going to have to substitute in like we did here. Okay. Finally, this is the last one that I'll do with you, and then I'll show you the last question in the packet here is actually an old homework question. So maybe you'll recall it once you see it. But this one is a conical tank of diameter 20 feet. Has a depth of 8 feet. The point of the cone is pointing down. If the water is leaking out at a rate of 5 cubic feet per minute, determine the following when the depth of the water is 6 feet. Okay, so here's my conical tank. The diameter is 20, so I probably am going to want to go to radius of 10 here. Okay, and the height is 8 feet. And eventually we're going to have to figure out something when the depth of the water is 6 feet, right? So we're going to have to eventually have a depth that's defined right here. So the first thing we want is the velocity of the top of the water. So the velocity of the top of the water is going to be the rate of change of how the height is changing as time goes on. So if we think about the volume that we're given here, we're given that dV/dt is, well, we're leaking out at a rate of 5 cubic feet per minute. So that's going to be a negative 5 there. We want dH/dt, when the height is 6 feet. Okay, so we've definitely got our given want when here. We know that volume equals, for our cone, 1/3 pi r squared h. But notice how I want dH dt given this value of h, and we know that our volume is dependent not only on h, but also on r. So we've done this before in other similar cone type applications where we have to set up a proportion that, in general, what is the ratio, what is the radius in terms of the height of this cone at any given time? Okay, so in order to do that, we can set up, because of the similar triangles here, we can set up a proportion. So we can say that r is to 10 as the height here is to the total height of 8. So if 8r is equal to 10h, then r would equal 10/8 or 5/4 of h. Okay, so I'm going to go ahead and plug that in then. For r. And before I find the derivative, probably just clean that up a little bit, right? Squaring this would be 25 over 16. If I bring that all the way to the front and multiply by 1/3, it would be 25/48. So the volume would be 25/48 pi times h cubed. Okay, now that we have this volume all in terms of the height, we should be able to pretty easily find the derivative and find dH dt based on the given dV dt at that height of 6. So therefore, dV dt equals, if I use the power rule here, that's going to become 75/48 pi h squared dH dt. And then we've got our change in volume is -5 when the height is 6, 75/48 pi times 6 squared dH dt. Okay. And if we start kind of throwing things over to the other side, right, divide the 36 over, multiply by 48 over 75, divide by pi. In the end, I'll let you kind of do some of the simplifying if you want to double check me here. dH dt winds up being in simplest form -4 over 45 pi, and then the units here would be feet per minute. Okay, so dH dt is that we're dropping, the surface is falling at that rate. Okay. So even though the surface is falling at that rate, the next question is a little bit different. It says, what's the rate of change of the surface area? Okay, so the surface area would be, the area of that circular piece as it's falling along the inside, not how it's changing, the rate of change of the height. But for part B, to find the rate of change of the surface area, we're going to say that area is going to be pi r squared. And therefore, the rate of change of that area would be 2 pi r dr dt. So we have a little bit of a slight issue here in that we don't know dr dt. We just did some really good work to find dH dt, but go back to a few moments ago, when we knew that the radius is 5/4 the height. So based on that relationship, I think we can easily establish dr dt right here by saying, hey, if the radius is 5/4 the height, then dr dt is equal to 5/4 dH dt. Well, that's pretty great because I know what dH dt is at this moment. So if I replace 5/4 times dH dt for dr dt, we can then pretty easily sub in here. Oh, and I guess we have to know the radius at that given moment as well, right? So when the height is 6, if you plug that in for height here, you're going to get the radius is 30 over 4, which reduces to 15 halves. So at this moment, when the height is 6, we know that the radius is 15 halves. And we know that dr dt, according to this relationship, is 5/4 times dH dt, which is -4 over 45 pi. And if you do a lot of canceling here, so this pi and this pi go away, and this 2 and this 2 goes away, and this 4 and this 4 goes away, and gosh, there's a lot of things that cancel. 15 goes into 45 3 times, so we have that negative on top, -5/3. Okay, so this would be -5/3. And since this is an area that's changing, it's square feet per minute would be the correct units here. Okay. So last but not least, we have to figure out in the last instance how fast the water is moving down the tank's side. So what we're looking for here is the rate of change of how fast the water is sliding down here. So we're going to need another variable. Let's call that z. And once we have that defined as z, now we can see we're just going to use these three variables and do some quick Pythagorean theorem there. So for part C, we're looking for dz dt, given that r squared plus h squared equals z squared. Let's see if I can really squeeze this in here. So it'd be 2r dr dt plus 2h dh dt equals 2z dz dt. We've seen this happen in other instances where when you have a Pythagorean theorem example like this, that those 2's will nicely cancel out. So the 2's all go away. And the other nice thing is at this moment, we know all these values. Maybe we know all these values. We don't know dz dt, that's what we're looking for. We can find z given our radius and height. Okay, so we're trying to do this when the radius is 15 halves. dr dt we just found a second ago was negative, it was this value right here, right? So what would that have simplified to with the 4's canceling out? dr dt would reduce to negative 1 over 9 pi. Okay, so that was just looking at this part of dr dt right here, plus h, which is 6, times dh dt. dh dt we found earlier is negative 4 over 45 pi. So we got to find z, which we can do pretty easily. And then we would divide that over to the other side. How would we find z? Well, using Pythagorean theorem at this given moment in time, we would solve that and eventually simplify z to be the lovely value of 3 radical 41 over 2. Okay, so I'm not doing the algebra there to show you the Pythagorean theorem. Hopefully you guys trust me on that, but that's what the value of z is. Okay, so when everything is cleaned up and simplified and you move this over to the other side and get dz dt alone, dz dt winds up equaling negative 41 over 45 pi radical 41. It's a lovely rate, isn't it? And that's in feet per second. Okay, so that's the rate at which the water is sliding down the side of the tank. So a lot of moving pieces to that, literally, right? We got things moving down the side. We've got, you know, the water, the rate at which the height's changing, the rate at which the surface area is changing as time goes on. So there's definitely a lot going on there, but hopefully the algebra all makes sense in terms of the setups. This one was unique in that to get dr dt, we had to go back to this relationship. I'm not sure how much we've done like that quite yet, but hopefully using this relationship, that makes sense. And especially since we already knew dh dt, we can easily sub in and make the appropriate substitutions in all these steps along the way. So if you have questions about this, please check in with me about it tomorrow. This last question is a homework question that you have hopefully seen as far as some coffee dripping down from this conical filter into the cylindrical coffee pot. So if you have questions about this, I'm going to show the answers to it tomorrow, but maybe give it a shot on your own, see if you can figure out how fast is the level in the pot rising, and then how fast is the level in the cone falling at that point. So go over that first thing tomorrow. We'll do some other review practice to get ready for the next quiz. Have a great day. Let me know if you have any questions.